In the previous video, we discussed two concepts, a point of a pointer and the pointers and functions. In this last video for the theory part, we are going to look at the dynamic memory allocation. We stated at the beginning of our presentations that C++ has got two types of memories. We have static memory and static memory, which is called, of course, stack memory, and we have dynamic memory. We've been working with static memory from the beginning of our programming journey in first year when we were introduced to variables, all the way up to previous video where we are working with the pointers, functions, etc. The pointers that we've been creating have been created on the stack memory. Whether we declare a variable or we declare a pointer, both were stored on the stack memory. But here we have a different concept altogether. We want now to look at a variable that has been declared and stored on the heap memory. Okay, so we've been creating variables on stacks this far. So if you have a declaration such as this will create a variable x on a stack, and the memory allocated for variable x on a stack will be deallocated or freed when the function in which x is declared finishes execution. That's what we said. When that particular frame is destroyed, everything under that frame is going to be destroyed as well. So when a program is being started, the static memory, which we call a stack memory, is set aside in advance for all the variables declared. So it looks at all the variables that have been declared in our program, and the program will ask the operating system to allocate enough memory that can be used for all the variables. So this is called static memory. So this static memory is actually known in advance. The dynamic memory, on the other hand, is not known. In most cases, we use dynamic memory during the runtime. But for the programs that we've been running, it means the variable memories were actually known before the program actually is run. So we are able, or the programs were able to secure enough memory, and that gives the program assurance that during the runtime of the program there will be enough memory for that program, because the memory is never changed. It's already allocated before the program is actually run. If there is not enough memory, then the program does not run at all. It will complain of insufficient memory. But the moment the program runs, it means enough memory is already allocated for that. If the program is actually using the static memory, if the program is actually using the memory of a stack, that's it. But sometimes we may need to request memory during the runtime of the program. We may not know how much of a memory we need. For example, when you are creating an array, we've been creating an array with array size specified, and that array size is a constant. It has to be known before the running of the program. But we are saying there will be times when you don't know how many elements will be needed. So for that, we may need to allocate dynamically depending on the situation. When somebody runs a program, you may want to create an array for example, maybe grades. We may not know how many students will be in that class. If we have a program that should be capturing grades and calculating average for the grades of a class for a certain module, so we may not know how many students will be there in the class. If we had known that it will always be 20, then we would have declared our array to be of size 20 as a static memory. But because it may not be possible, then this allocation of the memory for the array, the size of the array, would be done during the runtime, and that calls for dynamic memory allocation, so that we can create enough memory depending on the number of students for that class. Somebody will run the same program and will create maybe an array with a number of students 100, another one with a number of students 20. So this memory can be allocated during the runtime. When we are compiling our program, nothing of that sort will be known. So the memory that has been allocated during the runtime is called dynamic memory allocation. This is allocated using the new keyword. So the new keyword will actually return the address of the memory allocated. This memory is allocated in a heap, and the address for that will be returned. And we can now use a pointer to keep the address returned, and we use the pointer to assign the value to that address or to receive a value from that address. We cannot use the variable because there will be no variable name, a normal variable name, but a pointer variable. So here is an example of how you can create a dynamic memory. A memory that will be created when our program is running. It will not be known in advance, but during the running of our program. Of course, this does not give assurance to our program for the memory. So we can have our program running and it will try to request a memory, and maybe the memory will not be available. So our program may fail. But here we're just demonstrating how we can do that. And because these days we have enough memory, we have big RAMs, this is becoming less of an issue as compared to the early days of programming, where physical memory or primary memory was so limited. So if we want to create a memory on the heap, we use the new keyword. So this statement is going to create a variable for the integer. It's going to create a container for the integer that can be used to store an integer. And the address will be returned. And we cannot keep that address in a normal variable. We can only keep that address in a pointer. So we need to receive it as a pointer. So the new int is going to create the integer variable, so to say, and the address of that integer variable is going to be kept in a ptr. So memory allocated, after using it, because we have allocated our memory using new, we have to make sure that we manually delete. So the memory allocated in a heap should be manually deleted, and we use the keyword delete, and you specify the pointer that was pointing or that is storing the address of that memory or of that variable. So delete ptr is going to delete this location, is going to free this location. Here we have an example which is showing a complete picture. We have a function and we are creating an integer, and we can now assign a value 25 to this, and we're going to assign that using the dereference operator. So the dereference operator, it means it's pointing to that, and we are putting the value 25 to that. So we have declared this and we have it as a pointer, and we are assigning the value to that. So we are assigning this to the address pointed by this. And after assigning and using that in our code, then we can delete it before we exit the function. We can delete this. Okay, so we said something about the arrays, that we're required to specify the size of an array, but in practice we may not always predict the number of items. Of course, there have been some ways of doing it. We would just come up with an array with a very big size. For example, maybe a size of 1000, knowing that we may not have maybe a program with 1000 students, or maybe a size of 10,000, knowing that we may not have a program with the programmers in a course with 1000 or 10,000 students. But probably that's a waste of resources. If on average our maybe classes are 100, and we declared a variable, an array of 10,000 elements, just in case we have a very big class, then we are wasting our resources, memory. But we can use a dynamic memory allocation to just allocate enough memory during the runtime. So if we are not sure of how big that array should be, then we can think of using a dynamic memory allocation or the heap memory instead of using the static memory. So this is how you can do. This size can be from the user, can be whatsoever, maybe from a database. You count how many records are there and you want to take them and put them into an array. So you can create a dynamic array using this syntax. You have an array of size, blah, blah, blah. This can be 10. And this is going to create the array of 5 elements in our case. And the address of the first element will be returned. So we are storing it in a pointer. And now you can use this to access the elements of this, or to assign values or elements to this array. After finishing using that particular array, you can delete, because this one is now an array, you need to delete it using this. Previously we are just delete the pointer name, but here, because it's an array, you need to specify the square bracket so that it can delete all the elements for that, all the spaces for that array. There are some other concepts related to dynamic memory allocation. The first one being memory leak, which is one of the most common problems that programmers face when we are working with the dynamic memory. Because we have to manage the memory ourselves, sometimes we may forget, for example, to delete the memory after using it, and that can bring some problems. So always make sure that the dynamic memory allocated is actually deleted before you have a return statement, for example, or before the function finishes execution. Because if we don't do that, then we'll have dynamic memory allocated still existing even after finishing executing that statement, that function. As I stated earlier, the lifespan of a dynamic memory is beyond the function. So it can still be in existence, but we have exited the function. There will be no way for you to actually use that memory again, because you have lost the reference to that memory. And this will actually make the memory which was allocated not available to other programs, a situation which we call a memory leak. Here we are just demonstrating how a memory leak can be, of course we are intentionally doing this, how we can have a memory leak in our program. So here we have a memory allocated, and if true, return. This statement down here will not be executed in this case. Our program will be exiting at this point. So the memory that has been created here is not deleted, because the statement is beyond that. And it's returned to probably the caller, which might be the main function, and there will be no way for us to reference to this memory which was created because we will have lost this pointer, because the pointer here is on the stack memory, but the actual memory is the dynamic memory allocated. So the pointer is stored on the stack. So the moment we finish executing this one, the PTR will be destroyed, but this memory that was created to store an integer will still be in existence. So this is a memory leak. Another similar concept is that of dangling pointer. After a dynamic memory is actually freed, its pointer has still an address of the memory. So freeing dynamic memory is one thing, and making sure that the pointer does not point to that address which it was pointing is another thing. So it will still be available and pointing to the memory, but now that memory that is being pointed to, the address is pointed to, has been freed. So we have a pointer which is pointing to the allocated memory, and this situation is called the dangling pointer. It's a similar situation which we can have if you are returning an address of a local variable in a function, because that local variable, its memory will be deleted, but we are still pointing to that if we return the address of that. So that one is a dangling pointer. So a pointer is said to be dangling if it is pointing to a memory location that has been freed by a delete keyword, but we haven't reset the pointer. So there will be a problem if you're accessing a dangling pointer, because you might be accessing maybe an address which has been allocated to another program. So that might be a problem. We may be accessing the value which is not ours. So you can avoid that by making sure that you reset your pointer to 0 or null as soon as you free the memory. So soon after the deleting the memory, you need to set it to 0 to avoid dangling pointers. So you can have these two statements always appearing together to avoid dangling pointers. So here we can appreciate that working with the dynamic memory is a little bit of work on the side of a programmer, because you have to manage everything by yourself. But of course it gives you more freedom of how you can handle your memory and how you can actually have memories allocated during the runtime. Yeah, so that's what we wanted to have or discuss under pointers. These are very important concepts. We may cement some of what we have discussed here in our practical videos. But thanks for watching. Make sure you understand each and every concept that has been discussed in these videos. Remember, we started our journey by looking at a variable in general. That a variable has got a name, has got a value, and has got an address. And we also looked at the dynamic memory, the two types of memories that are managed in C++. We have static, which we call stack memory, and the dynamic memory, which is a heap memory. So we've gone through the concepts of a pointer, pointer arithmetic, a point of a pointer and functions, and all those other aspects. And finally, we looked at dynamic memory allocation. Should be very comfortable with using pointers and be very comfortable using dynamic memory allocation. It's very important for you. Thank you, and see you in the practical videos.